Section 14.5, surface area. Now, I'm not going to go through the process of deriving this formula for you. You can look that up if you're interested in those details. But just to give you a feeling for what's happening, suppose I have some surface, right? And I'm interested in finding the surface area. I can take a little slice of that surface area. That is hovering above some region in space. Okay, so this is our region R. This is our little bit of surface area here. And this can be approximated with a parallelogram. Okay, and then we can find the area of that parallelogram, which is going to lead us to our surface area. If we were to define two sides of this as vectors, then the area of that parallelogram would be equal to the magnitude of the vector u crossed with the vector v. Right? So that magnitude of that cross product is what's driving this formula. So let me write that formula down for you. So if f and its first partial derivatives, I should say, are continuous on a closed region R, I should specify r's in the xy plane, just to be specific, some closed region R, then the surface area of the surface S given by z equal to f of xy, okay, over R, is given by the following. Surface area is equal to the double integral over R ds. So we're integrating over the region R with respect to the surface. That's equal to the integral over R of the square root of 1 plus the partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared dA. There we go. So that is our formula for surface area. I'll put a lovely box around that. All right, so you can definitely see remnants of the surface area function that you would have learned in Calculus 2 for finding that. These integrals can get quite grody, right? Like we can do some trig subs, that might become necessary, that sort of thing, to work these out. However, a lot of times with the surface area, we're looking for some kind of an approximation. So this is one of those rare instances where I feel that working the problem manually is good exercise, but isn't necessarily necessary. So we will probably be working some of these with our calculators, but I'd also like to go ahead and get some exact answers as well, just so that you can see that. Okay, so first example here. So we have find surface area. Before I continue, how you know if you need to give an exact answer or a decimal approximation. An exact answer, the question will say give an exact answer. Okay, so that's looking for an exact answer, including any fractions, square roots, things like that. For a decimal approximation, you'll specifically be asked to round to the nearest decimal place. So that's how you can usually tell when you need one over the other. All right, so find the surface area of the plane given by z equal to 2 minus x minus y, 2 minus x minus y, that lies above the disk x squared plus y squared is less than or equal to 1 in the first quadrant. Okay, so we have a disk of radius 1, x squared plus y squared is less than or equal to 1. So we have a disk of radius 1, and we're only interested in that first quadrant. Okay, so we're looking for the area of our plane lying above this. Now, you might think, well, wouldn't it just be whatever the area of that part of the circle is? And the answer is no, because if you were to take a plane and have it tilted, as this one is, have it tilted at some other angle, it's going to increase the surface area that lies above that. So you can kind of get an image of this from a shadow. If you hold a light above your hand, you'll get a shadow on the table. And as you rotate, as you turn your hand, what you'll see is the shadow covers different areas in the horizontal plane of the table or desk or whatever you're working on, right? So my surface area of my hand's not going to change, but if I tilt my hand, its shadow looks a lot smaller than the actual surface area. So I don't know if that made a lot of sense, if that came through over the video, but hopefully you can kind of imagine what I'm getting at there. Okay, so f of xy is equal to z is equal to 2 minus x minus y. So we're going to need fx, so that's -1. We're going to need fy, that is -1 also. All right, so the integral for our surface area here is going to be the integral over our region R of the square root of 1 plus f prime, nope, that would be a calculus 2 statement of f, the partial of f with respect to x squared plus the partial of f with respect to y squared ds. Sorry, dA. There we go, dA. My bad, sorry about that. Okay, so we've got f sub x, we've got f sub y, we found those. Now what we have to figure out is how do we describe our region R? How do we describe that? So there's a couple of different ways that we can do that. So the first is that this circle is given by x squared plus y squared is equal to 1. Okay, so that's our circle. So now we have to figure out how we're going to describe this thing. So this is x and this is y. Okay, so I'm going to redraw it. This is 0 to 1, this is 0 to 1. And we just need to decide what we're going to integrate with respect to first. It doesn't really matter which one we do, whether we want dx or dy. It's irrelevant. So here's what I'm going to do. I'm going to go ahead and set this one up so that we have our integral. And I'm going to integrate it with respect to x first and then y. And the reason I'm choosing to do this is simply because this is in the previous video, most of our examples we were integrating with respect to y first, and I just want to show you that we can do this with respect to x. So my boundaries on y are going to be constant because that's my external integral. So the outside most integral, it's going to be constant bounds of integration. Whew, gotta get my mouth working here. All right, so bounds of integration on y. So those are going to be constant, and this is my y direction, right? And this is my x direction here. So we have got y going from 0 to 1. So those are going to be the boundaries on y. Now, the boundaries with respect to x, so how far are we moving from left to right, those are going to be given by a lower boundary of 0 and an upper boundary of the curve. Okay, so that curve was x squared plus y squared is equal to 1. So lower boundary 0, and then the upper boundary, or the rightmost boundary, that's going to be given by this. So we need to solve this. This is an x value. We need to solve this for x. So we've got x is equal to plus or minus the square root of 1 minus y squared. Now the only thing about that, though, is that that's positive and negative. That's two different parts. So we only need the positive because we are in quadrant 1. So we are going to use, let's see, I'll write this down. We only need the positive square root of 1 minus y squared because we are in the first quadrant. So then our upper boundary is going to be the square root of 1 minus y squared. Okay, so then here's what we have. We have 1 plus -1 squared plus -1 squared. So that was our 1 plus f sub x squared plus f sub y squared. And now we're going to integrate that with respect to x. All right, so this is going to be the square root of 3. So this is the integral from 0 to 1 of the integral from 0 to square root of 1 minus y squared of the square root of 3 dx dy. Integrating square root of 3 with respect to x, pretty straightforward. It's going to be root 3 times x, evaluated from 0 to the square root of 1 minus y squared dy. So that's equal to the integral from 0 to 1 of the square root of 3 times square root of 1 minus y squared minus 0 dy. So that's the integral from 0 to 1 root 3 square root of 1 minus y squared dy. All right, so this would be pretty easy to put into our calculator. However, I do want to go ahead and just help you remember how we would have solved this in a Calc 2 class. So depending on your instructions, if I ask you for an exact answer, I would expect you to follow, some procedure to get there. If I ask you for a decimal approximation, that's just asking you to put it in your calculator, right? So let's go ahead and do this. We're going to solve this using a trig sub. So we're going to use a trig sub. And because we have something of the form a squared minus u squared, we want to let our variable be equal to sine of theta. So we're going to let y equal to sine of theta. Okay, so then dy is going to be equal to cosine of theta d theta. So now we can make our trig substitution, but before I do that, I want to go ahead and draw the triangle that's kind of driving this substitution. So we have our right triangle with our angle theta here. If the sine of theta is y, that is the opposite over hypotenuse. So y is y over 1. So the opposite leg is length y and the hypotenuse is length 1. That makes our adjacent leg to theta here the square root of the hypotenuse squared minus y squared. And so you can kind of see that showing up here in our triangle. That's what was in our integrand, and here we see it showing up in our triangle. So that's going to be helpful. Okie doke. So let's go ahead and make our substitutions. So this then is going to be equal to the integral from 0 to 1 of, it's not 0 to 1 anymore though, is it? Because we're making a substitution. So let's just leave the boundaries off for the moment, and when we go back to y, we'll put in our 0 to 1. All right, so root 3 can just come out as a constant. And then square root of 1 minus y squared, that's going to be the square root of 1 minus sine squared theta. And then dy is replaced with cosine theta d theta. Okay, so I'm just doing a trig substitution. This is something you should have seen before. I'm substituting sine theta in for y, cosine theta d theta in for dy. Okay, all right, so this is going to be the square root of cosine squared of theta times cosine of theta d theta. So that's square root of 3 times the integral of square root of cosine squared theta is just cosine theta. Cosine theta times cosine theta is cosine squared of theta, d theta. We want to use our substitution here, our trig identity. So cosine squared of theta is 1 plus cosine of 2 theta over 2. So this is root 3 times the integral of 1 plus cosine of 2 theta over 2 d theta. Okay, so I'm going to bring the 2 and the denominator out, so we'll get root 3 over 2 times the integral of 1 plus cosine of 2 theta d theta. Evaluating that integral, we're going to get theta plus 1/2 sine of 2 theta. Okay, and then we need to switch all of this back to y's. We need all this back in terms of y's. Problem is, sine of 2 theta, I don't really have that, because let's go back to our triangle. Okay, here's theta. I've got y, 1, square root of 1 minus y squared. So this triangle is where I'm going to get any trig identities back out. So any trig subs that we made, this triangle is going to allow me to go backwards, because we've got SOHCAHTOA, Oscar had a heap of apples, however you remember sine, cosine, and tangent, we're going to be able to pull them out of here. Okay, the problem is I don't have an angle 2 theta. I just have angle theta. So we're going to have to convert sine of 2 theta back to angle theta. So this is root 3 over 2 theta plus 1/2 times do a parenthesis there. So sine of 2 theta is 2 sine theta cosine theta. Okay, and that comes from the sum identity. So if you have the sum of angles, sine of the sum of 2 angles from that identity. So there's that. So then we have that, and then I can switch all this back to y's, and then I can evaluate it from 0 to 1 as we were supposed to do from the beginning here. So this is root 3 over 2. Theta is what? Well, theta is in this relationship, sine theta equal to y. That was our original substitution. So that makes theta equal to the inverse sine of y. So theta is the inverse sine of y, plus the 2 and the 1/2 cancel. Sine of theta is going to be y, opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, so that's square root of 1 minus y squared. And that's being evaluated from 1 to 2. So again, if this is a bit mystifying, it's a trig substitution. It's something you should have seen in Calculus 2. If you don't remember it, let me know. I'd be happy to go over it with you, or you can look it up, watch a video on it, see Paul's online notes, OpenStax. Any of those resources would be good. Okay, so here's this. And I can evaluate that. So this is root 3 over 2 times the inverse sine of 2 plus 2 times the square root of 1 minus 2 squared. You guys, I don't know where 1 and 2 came from. I was just looking at this like, uh-oh, that's a problem because I can't have a negative number under the radical, right? But then I go back and look and it's like, wait a minute, no, I was supposed to evaluate this from 0 to 1. So I apologize. I'm not sure where 1 and 2 came from. It should be 0 to 1. 0 to 1. There, that's better. So then I will correct all of those entries. So this will be sine inverse of 1 plus 1 times the square root of 1 minus 1 squared. All right. Minus, and now we put in our 0. So that'll be sine inverse of 0 plus 0 times the square root of 1 minus 0. Okay, so let's see here. This goes to 0 because square root of 1 minus 1 is 0. This goes to 0. So all I have left then is root 3 over 2 of sine inverse of 1. Well, what angle has a sine of 1? Well, pi over 2. So that's pi over 2 plus 0 minus sine inverse of, not inverse of 1. It should be inverse of 0, sine inverse of 0. That's what we were plugging in here, right? It was a 0, not a 1. Gracious, gracious, gracious. Okay. The angle whose sine is 0 is 0, so that'll be minus a 0 plus nothing, plus 0. So this comes out to be root 3 over 2 times pi over 2, which is equal to root 3, well, I'll put the pi first, pi root 3 over 4. And there is the exact surface area for this surface over this region, the quarter circle. So let's go ahead and do another example. Oh, by the way, if I ask you to do something like that on the exam where I want you to do a trig substitution, which I won't, but if I did, I would provide you, with the trig substitution, I would say use this as your substitution. But I don't have any intention of giving you a trig sub on the exam. If that would be necessary, I would very likely just ask you to give me the decimal approximation from your calculator. Okay, so let's do another example. Let's find the area of the surface given by f of xy equal to 1 minus x squared plus y above the triangle with vertices 1, 0, 0, 0, negative 1, 0, and 1, 1, 0. All right, so keep in mind that we have our region in the xy plane. So these points are creating a triangle in the xy plane. We should have a look at those. Okay, so I'm just going to look at the xy plane here. We have the point 1, 0, 0, negative 1, and 1, 1. Okay, so there's our triangle with our given vertices. Now we are going to need to be able to bound this region, and so to do that we're going to need equations of our lines. So I'm going to draw each line with a different color. So this one in green, that is part of the line x equal to 1. Right? It's a vertical line through the point, through every point where x is equal to 1. Okay, now the pink, that'll be this line. So we are going to need an equation for this line. All right, so we have 2 points. So it's going through the point 0, -1, and through the point 1, 1. Okay, so we can find that line. Our slope is going to be equal to 2 over 1. So that's 2. So we have y minus, I'm just going to use the top point here, y minus 1 is equal to 2 times x minus 1. All right, so y is equal to 2x minus 2 plus 1 will be minus 1. Okay, so there's 2x minus 1, so there's that one. And then that's the pink line. So let's do another color. Let's do orange for the third line here. So this is going to the point 0, -1, and also 1, 0. All right, so we'll do the same thing. So our slope here is going to be 1 over 1, which is just 1. Okay, y-intercept is -1, so we've got y equal to x minus 1. Okay, so we have those. Then we need to figure out how we're going to define our region. So one good thing to notice here is that we consistently have the same line above another. So if we look at green, the green portion as being vertical, which it's supposed to be vertical, it's a little bit off kilter, but it's supposed to be a vertical line. What we see is that we have y above y. We have the pink above the orange at all times. So let's notice that y equal to 2x minus 1 is greater than or equal to y equal to x minus 1 for all x between 0 and 1. Okay. Okay, so it looks like we can define our region if we integrate this dy dx. We can identify our region as being that space where y goes from 2x, I'm sorry, not 2x, undo, x minus 1 on the lower boundary to 2x minus 1 on the upper boundary. All right, then x is going to be running from 0 to 1. So then we just need to set up our integrand here. So it's 1 plus, we need f with respect to x, the partial of f with respect to x squared, plus the partial of x with respect f with respect to y squared. Man, I have mush mouth tonight. Okay, so continuing onwards. So our original function here was f of xy equal to 1 minus x squared plus y. All right, so the partial derivative of f with respect to x is -2x. Partial derivative of f with respect to y is just 1. So what we get here for our integral is our integral from 0 to 1 of the integral from x minus 1 to 2x minus 1 of the square root of. Okay, so 1 plus -2x quantity squared plus 1 squared dy dx. All right. So that's the integral from 0 to 1 of the integral from x minus 1 to 2x minus 1 square root of 1 plus 4x squared plus 1 dy dx. So I can pull out a root 2. Let's not skip steps. Square root of 2 times 1 plus 2x squared. Okay, so if I add 1 and 1, I get 2. Factor out of 2, I get 2 times 1 plus 2x squared. dy dx. So we can go ahead and take that root 2 out. So that's going to leave us with the square root of 1 plus 2x squared dy dx. Alrighty. Now, it is an unfortunate fact that many people, even in a Calculus 3 course, do not realize that you cannot distribute a square root across plus signs. Right? So let me just refresh your memory here. If you have the square root of a times b, that's a product. That's the square root of a times the square root of b. Because the square root's an exponent, right? A rational exponent 1/2. And a product raised to an exponent is the exponent on each element of the product. Now, that is not the case for a plus b. That is not equal to the square root of a plus the square root of b. It does not work like that. This is no good. So many people do this, even in a Calculus 3 course. So please be aware of that and watch your algebra. So just to be clear, that is not true. This is not an equality. This is false. So please be very aware of that anytime you're dealing with square roots, especially inside of radicans. Okay, so this is going to be, don't want red, it's hard to see. So this is root 2 times the integral from 0 to 1 of the square root of 1 plus 2x squared times y, we're integrating with respect to y, dx. Ooh, but we have to evaluate that y. Let's do that. So that is being evaluated from x minus 1 to 2x minus 1 dx. There we go. Okay, so root 2 times the integral from 0 to 1 of. So these are y values, right? So we're replacing y with those values. So this is square root of 1 plus 2x squared times, all right, so we plug in the y, 2x minus 1 minus x minus 1 dx. So that's root 2 times the integral from 0 to 1 of the square root of 1 plus 2x squared. And then in here we have 2x minus x is x. Negative 1 minus negative 1 is nothing. It's 0. So there we have it. Okay, so this is one that's very easy for us to integrate by hand. We'll just do a u substitution. Let u equal to x, then du is equal to dx. I just did that, and that is so not what I meant to do. Back the train up. There we go. All right, so we're going to let u be equal to this radicand right here, 1 plus 2x squared. And the reason for that is because then x dx will be in the derivative of u. So du is equal to 4x dx. There's our x dx. All right, so then that implies that 1/4 du is equal to x dx. So we have our two substitutions. We've got x dx getting replaced with 1/4 du, and then we have 1 plus 2x squared being replaced by u. Okie dokie, so this is root 2 times the integral of. Now, if we are going to replace x's with u's, we have to replace our boundaries. So remember, these are x values. So if I want to change them to u values, I simply substitute the x value in and find the u value. So if x is 0, that makes u equal to 1, because 1 plus 2 times 0 is 1. If x is 1, that makes u equal to 3, right? Because I'm going to take my 1, plug it in here for x. We've got u is equal to 1 plus 2 times 1 squared. That's 1 plus 2 is 3, okay? So those are our bounds of integration when we're integrating with respect to u. So this is going to be the square root of u times 1/4 du. Pull the 1/4 out, we get root 2 over 4 times the integral from 1 to 3, root u du. So that's root 2 over 4 times, okay? So u, square root of u is u to the 1/2, add 1, that's u to the 3/2, divide by 3/2, we get 2/3 u to the 3/2, evaluated from 1 to 3. So this is going to be root 2 over 6 times 3 to the 3/2. No, I'm okay. Whew. I thought I forgot to put a power on the 2/3, but I didn't. We're okay. All right, so 3 to the 3/2 minus 1 to the 3/2. And so what we get is the square root of 2 times 3 to the 3/2 minus 1 divided by 6, or root 2 times 3 to the 3/2 minus root 2 over 6, which will simplify just a little bit further and give us, let's see, 3 root 6 minus root 2 over 6. Okay, and that would be our final answer. So on an exam, you could stop right here. I'd be perfectly fine with that. That would be fine. For that matter, on the exam, if you got to here, I'd probably be okay with that. All right, and of course, sometimes it is easier to describe our region in the plane as a function of polar coordinates. So let's do one more example where we will convert to polar coordinates. So let's find the area of the surface given by z equal to 1 plus x squared plus y squared lying above the disk given by x squared plus y squared is less than or equal to 1. Okay, so again, we have the unit circle. So all these x squared plus y squareds kind of lend themselves to say, hey, you know what? We could definitely do some polar changing here, changing to polar coordinates. So let's see how we would do that. First things first, let's sketch our region R. So we know it's the unit circle. And this is x squared plus y squared is equal to 1. So the upper half of that would be y equal to the square root of 1 minus x squared, excuse me. And the lower portion would be y equal to the negative square root of 1 minus x squared. Oh my goodness, Becky, I'm going to have to stop recording. Okay, let's keep fighting through this here, see what we can do. So this is going to be negative square root of 1 minus x squared. Okay, so we could set up an integral in rectangular coordinates. It's not going to be pretty, but we could do it. So we could set this up so our region would be going from the lower boundary to the upper boundary in the y direction of negative square root of 1 minus x squared to positive square root of 1 minus x squared. Y would be going for x would be going from negative 1 to 1, and then we would have our square root and we would put in our derivatives. So 1 plus 2x squared plus 2y squared dy dx, right? And that's not going to be a really pretty integral to do like this in rectangular coordinates. However, it does lend itself nicely to conversion to the polar coordinates. So let's take a look at that. So first of all, if we do this in polar coordinates, I'm going to switch over to green. Our theta goes around 2 pi, and our radius is constant at 1. R equal to 1. So that's nice. So we would set this integral up, and this would be our thetas for the external. This would be our r's for the other one, right? So our radius for this is going from 0 out to 1, right? So there's no formula there. I don't have to have r as a function of theta, anything like that. And theta is going from 0 to 2 pi, right? Then we need to look at our integrand. Well, in rectangular coordinates, we had the square root of 1 plus 4x squared plus 4y squared dy dx, right? Well, that can be rewritten as 1 plus 4 times x squared plus y squared. Well, x squared plus y squared is replaceable by r. So this will be the square root of 1 plus 4 r squared. And as we have said before, when it comes to changing variables to polar variables, we have to replace dy dx with r dr d theta. R dr d theta. Do not forget the r. And now we can integrate this one pretty easily with a standard u substitution. So this is the integral from 0 to 2 pi times the integral from 0 to 1 of r times the square root of 1 plus 4r squared dr d theta. All right, the reason I put the little r here that was part of r dr d theta as, you know, that change for our area of the region, I went ahead and moved that to the front because that's usually where we see it. So I'm going to let u be equal to 1 plus 4r squared. Then du is equal to 8r dr. So 1/8 du is equal to r dr. And so there's our substitutions. So this is going to be equal to the integral from 0 to 2 pi of the integral, and we're changing to r, so this is now going to be 1 plus 4 times 1 squared, so that'll be 5 as our upper boundary, and then 1 plus 4 times 0 squared will be 1 as our lower boundary. Okay, so then r dr is replaced with 1/8 du, so that's going to be the square root of u du. Okay, so let's make sure we have all of our substitutions. So I've got r dr being replaced with 1/8 du, and then I've got 1 plus 4r squared being replaced with just u. So it looks like we have our substitution in place. I'll drop the d theta. Let's get that d theta back in there. Okay, so this is our integral from 0 to 2 pi of, so integrating this, we get 1/8 times 3 2/3 u to the 3/2, evaluated from 1 to 5, and then we'll take that integral with respect to theta. So integral from 0 to 2 pi of 1/8 times. Putting in the 5, we get 2/3 times 5 to the 3/2 minus 1 to the 3/2 is just 1 d theta. So we have a constant, 1/8 times 2/3. I'm going to pull that out. So that's going to be 1/12, because the 2 will cancel with the 8, right? So that's 1/12 times the integral from 0 to 2 pi of 5 to the 3/2 minus 1 d theta. So that's going to be 1/12 times 5 to the 3/2 minus 1 times theta, evaluated from 0 to 2 pi. So when I plug in a 0, it'll zero out. So I end up with 1/12 times 5 to the 3/2 minus 1 times 2 pi. So the 2 will cancel there, leaving me a 6. And what we end up with is 5 to the 3/2 minus 1 times pi divided by 6. And we will put a box around that. Okay, so that's going to be our last example for this section. So you can kind of see how we can convert two polar variables and do our integration that way to make it a much nicer, easier integral. If you have any questions, as always, please let me know. And yeah, that's this one. Y'all have a good one. Thanks.